Good afternoon, everyone. I I hope my screen is visible to you and I'm audible. Yes. We basically started uh, the economic load dispatch problem earlier, and let's take an example. Let's assume there are basically two generators, and let's say the cost functions are basically 0.006 P1 square plus 2P1, and you just feel free to ask. If you have any question, you can either put them in the chat, or you can basically raise your hand, then I will unmute you and we can basically you can ask your questions verbally as well. Like, let's say this is my second generator, and 600, and certain limitations are there. So the demand is, let's assume, 200 megawatts, and our generation limits are basically, let's say, P1 and P2 are, if it is 200 megawatts, so let's keep it 150 megawatts. So let's assume this is one example, and if we try to solve this one, so we understood that, like earlier we written down objective function of cost minimization and subject to a power balance equation, and uh, and like limits on the power generation, so P1 and P2. So this data is provided here, and then we basically return a Lagrangian function. So instead of, like, Pi, I'm writing down all the variables here. So these are the three variables I have, and I can say C1 P1 plus C2. P2 is my cost functions plus lambda, and total demand minus P1 minus P2 is my generation. So then we were like writing down the KKT conditions as explained earlier for optimality. So delta L upon delta P1, and that will be basically equals to delta C1 P1 divided by delta P1 minus lambda. Okay, and in short, basically this partial derivative of the cost is like is called, also called as a incremental cost. So I would say IC of the first generator minus lambda. So this is our basically the first condition, and it should be equals to 0. So that is the condition 1. Similarly, we can write down del upon del P2, or let's the data is available, then why not writing down. So if you take a partial first order derivative of the above cost function C1 P1, which is given here, uh, you will get like 0 point, I think, 0 1 2 P1 plus 2 minus lambda equals to 0. Similarly, we can write down delta L upon del P2, and that will be incremental cost of second generator minus lambda equals to 0, and the condition will become 0 0.01 P2 plus 3 minus lambda equals to 0. Okay, so this is like with respect to two variables. We have another variable which is lambda, so delta L upon delta lambda, and that will be basically nothing but our power balance equation P1 minus P2 equals to 0. Here we have defined that the PD is, let's say, 200 megawatts, so it is 200 minus P1 minus P2 equals to 0. So these are the three equations. So equation number 1, equation number 2, and let's say equation number 3. If we try to solve these equations from these two, we can write down that the lambda is constant, so we can equate these conditions, and we can get a basically 0.012 P1, and this will be like minus 0.1 P2, and it will be 3 minus 2 1. So this will be the one equation. Another equation is this, so I can say this is like P1 plus P2 is equals to 200 of the demand. and like just to, if we want to solve it, let's say multiply with 0.01. Okay, 0.01, and if we add them, we will get 0.022 p1 equals to how much it is, 2 plus 3, and p1 will be 3 by 0.022, and you will get certain value for this one. I think you can suggest me the values, and whatever is this value, we can easily get p2 as well. Okay, so what will be this value? I think 3 upon 0.022. If anybody has the calculator with them, you can solve it. Let's solve it. So 3 divided by 0.022 is 136. So it's 136.36, and minus, so if that is minus 200 is roughly around 63.64 is the P2. And then if we use these values to calculate the lambda, so we can use either equation number 1 where we can put the value of P1, or equation number 2 where we can put the value of P2. So let's say this is 63, this multiplied 0.01 and plus 3 is roughly around 3.64 is the lambda. So this is some answer we are getting it. So this is how we solve this particular problem. If you see here, like this 136 and 63.64 both are within the limit. So like both the generators, we had a maximum limit of 150 megawatt. So they are nor violating the maximum limit and minimum limit. But can you, okay, let's say another case too, where the demand is, let's say how much, 400 megawatts. What will be the solution in this particular case? So I request all of you, if demand is 400 megawatts, what will be the solution? So these are the equations, and you can use those equations, and you can try to solve the answer. So basically, equation 1 and 2, we derived this particular equation, and with the equation 3, we placed it here. So instead of this 200, we can place 400. So what will be the demand in this particular case? So I think this 3 will become 5, if I'm correct. And what will be the value of P1? Can anybody calculate it? Like, so this is like, instead of 200, if it is 400, so 4, this will become 4, 4, 1 plus 5, this will become 5. And then we can have 5 upon 0.022. So how much that will be? Ratan? Yes, so Satya has calculated. So if this is the demand, just calculate P2 as well. So like, P1 you have calculated 227.2. So we can calculate P2 will be like, minus 400 minus this value. So that will be 227 will become how much? What will be the value of P2? 400 minus 227? It's, I think, 130. 172, 172.8. Yeah, so like with if I go with this figure 2.27, this much demand will come. And is this so? So if you look at these values, so it's like 5 divided by 0.022 is this, and minus 400 is 172.8 or 72 or something like that. So like approximation can be this value. So let's say these P1 and P2, and if you look at both the values, we had a maximum, like the constants was like P1 and P2, can maximum have 150 megawatt and minimum have let's say 20 megawatt. In this case, both the demands are more than this maximum limit. So what is the outcome, or what can we say about this particular case? So mathematically, if I talk about the solution is called infeasible. Infeasible solution. Okay, that a solution cannot be obtained because of these limit, and like both the generators can maximum supply 300 megawatts. So whatever the demand more than 300 can never be sold with this particular example. So what went wrong basically? I think some of you attended our system operation FDP as well. So I think you guys can answer it better, like way, that what went wrong here. And how we can obtain the solution in this particular case. Like something is wrong, it's somebody's fault, I think. And so who made a particular basically mistake, who made this mistake that we are not able to get a particular solution out of it? Yes, inequality constraint needs to be enforced. So it is quite evident that uh, with only two generators, we can never supply more than 300 megawatts. But whose fault it is? That if demand is 400 and there are only two units, and both of these units are not able to supply it. So yes, one comment is there, unit commitment. Thank you, Satya. So it's basically like system operators fault, we can say that if demand is more, he should have basically foreseen it and committed more number of units. So with this particular, I can say that like the economic load dispatch is performed after unit commitment. So first of all, like if we trying to operate our power system, we first commit certain units, and those units should be able to supply the demand. And if we don't have sufficient generation, then we have to curtail the certain demand, like load curtailment has to be done, and otherwise we will never get a solution of the economic load dispatch. So similarly, I can say that, like the same case will happen. Let's say if the demand is 30 megawatt, because the minimum is 20. So minimum both the units are going to produce is at least 40 megawatt. So for 30 megawatt, we have to turn off one more unit. And if we want to basically supply the 400 megawatt, we have to turn on one unit whose capacity is sufficient so that we can supply the 400 megawatt. So this is the one of the case. Now let's talk about another case for where the demand is basically, let's say 300 we can supply. So let's say at 280 megawatts are there. So in this case, what will be the answer? So we had above two equations. That first was, I think, 0.012 P1 plus 2 minus lambda equals to 0, and similarly like 0.01 P2 plus 3 minus lambda equals to 0. So out of these we have written 0.012 P1 minus 0.01 P2 equals to 1, and another equation was like P1 plus P2 was equals to, in this particular case, 290, and then we multiplied 0.01 0.01 and multiplied 0.01. So P1 will be how much? So divide, we already know it will be 0.022, and above will be like how much is the 2.9 and 1 is 3.9. So it will be 3.9 divided by 0.22. And if we calculate this one, it's basically at 290 is the demand, right? So it is basically 280. So in this particular case, it will be 3.8, and that will be basically 3.8 divided by 0.22 is 172. Further again, how it is coming the same value? 172.72. Okay, and then P2 will be minus 280 is the demand. So equals to minus 280. It is 107.28. Okay, so this is basically our P1 and P2. Now, if we look at that this particular demand has been reached to a maximum limit, we will not go with this particular solution. What we will do is we will enforce the limits. So P1 has to be made 150, and once P1 is there, the P2 will be automatically become 150 minus, so 280 minus 150. So how much it will be? So 8 and 5, 130. Okay. Now, when we calculate lambda, or I would not call it lambda now. I will call it lambda 1, which is equals to the incremental cost of 1. So if you go back, uh, this is what we have written here, that it is incremental cost of 1 minus lambda was equals to 0. So here, if I want to calculate incremental cost with the whatever solution we have obtained after enforcing the limits, uh, some incremental cost will come here, and then similarly some incremental cost will come from here as well. So if we look at these values, incremental cost was roughly around, I think, twice of A, and P1 plus B1, right? So if we put the values, what was the values? It's 0.012 P1 plus 2. So you can put these values 0.012, and P1 is 150 plus 2. So you can calculate this value, and if it is 0.012 into 150 and plus 2 is 3.8. So this value is basically 3.8, and if I calculate lambda 2, which is equals to IC2, and that will be 0.01 P2 plus, I think, 3, and that will be equals to, if I put the 130 here, 0.01 into 130, and plus 3 is basically 4.3. We obtained two lambdas. One is lambda 1 and one another one is lambda 2. So which one is system price? I have explained you that this lambda represents the system price. So which one is the system price? That is a question here. So if we talk about unconstrained case, when we are not imposing any generation limit, lambda, like with this particular solution, we can calculate a lambda, and that lambda is basically how much? It is, I think, 0.012 into 172.72, okay, and plus 2. So it was 4.07. So you look at this particular lambda, it was 4.07. Now we have obtained 3.8 and 4.3. So the thing is, this is unconstrained lambda. Now these two are when we have enforced the limit and obtained two different values. Here, if I look at this particular one, I will not call it basically. So it is not a system price, because system price is when we are basically not enforcing any limits, and this lambda is not true lambda, so I will not consider this one. And because it is with the maximum like enforce the particular limit. If you look at this one, it is still like we are not enforcing any limit, and it is whatever left with. So this will be our system price, our actual lambda. Okay, so this is our system price at lambda, I will call it. So I will use this as a lambda. Now what does it signifies basically? So when limits are not enforced, you can see that the system price was 4.07. So like the prices of like per unit or per megawatt is basically 4.07. But because of the limits, we have to reduce the quantity from 172.72 of the P1 to 150. So we are basically restricting a cheaper generator, and we are reducing the power output of the cheaper generator, and because of the physical limits of the power plant at the unit. So if cheaper generators are has been the power output of the cheaper generator has been reduced, some expensive generator should supply that one. So we can see that the second generator is supplying that one, and if some expensive generator is supplying, the system price should increase, which is also evident here that instead of 4.07, it has been increased to 4.7. Okay, and the same thing we can observe from these conditions which we have learned earlier, that whenever the incremental cost is less than the system price, so this particular one, we have to enforce the maximum limit, and whenever the incremental cost is more than the system price, we have to enforce the minimum limit. And if it is within the minimum and maximum limit, then the incremental cost will be equal to the system price. So the second generator basically have the minimum power output which is within the limit. So that's why we are basically calling this 4.3 as a system price or lambda. Okay, so far I think it is understood. So based upon the same philosophy, we can develop a method, and generally it is called lambda iteration method. Okay, so how lambda iteration method works, and I can say it can work in distributed fashion. It does not need any solution technology or nothing. So first of all, what we can do is uh, assume or basically broadcast certain lambda. Okay, so it is basically like assume initial lambda value. So let's say lambda naught has been assumed. Then we can calculate the power outputs, and you can see these are the formulas. So if I look at this particular first condition, I can calculate P1 is basically lambda minus 2 divided by 0.012. So in generalized way, I can say the quadratic cost functions has been assumed for the generator. So I can say P is nothing but the lambda minus B1 upon twice of AI, and let's if I keep it in terms of I like for all the generators, so I can calculate power output of all the generators like for all I set of, and I can calculate this one. Once I have calculated this one, I will try to enforce the limit. So like I will look for the check for minimum and maximum limits. So okay, one more thing is, whenever we are looking at these limits, if we are solving it just the way like an above we have discussed that we can solve them, and if multiple in last class as well we discussed that if multiple limits are being hit, we will first enforce the maximum limit, and we keep it that generator output as a constant. So once that generator output becomes constant, our optimization problem will again like we will put this the value of that particular generator, and our problem will will be reduced, and then we will resolve it, and we see if there are some other maximum limits are being enforced or not. Otherwise, then we will see some minimum limits are being enforced, If some minimum limits are being basically violated, we will enforce them as well, and then we will solve it. So this is like continuously iterative process. So for a very like small number of generators, we can solve it with like in a with a pen in our like paper on our paper. But lambda iteration, it is this method is basically programmable. You can write down there. So this is a programmable method. So here is basically if this lambda is basically, let's say, some optimal output is there, and we have assumed certain lambda. If this lambda is less than whatever is the optimal or whatever will be the final optimal lambda, if it is less than that one, so it means system is paying less. Okay. And if system price is less, by the simple rule of economics, we can say that if prices are less, generators will produce less. And it is quite evident from this particular equation. If lambda is low, pi will be low, because b and a are constant for a particular unit. So if pi is less, um, basically you further wants to increase the lambda. But now let's again come back to the limits, that if maximum limits are enforced, so if whatever is the ifp, if it is more than or equals to basically whatever is my pi max, then I will enforce this limit and I will put pi equals to pi max. If my pi is less than whatever is the pi min, in this particular case, I will keep pi equals to pi minimum value, whatever is the minimum. And otherwise, if it is like within the range, we will keep that particular value. So once we have this identified this one, we will calculate for error. Okay, so once we have enforced these limits, we will calculate some error, and that error will be whatever is the demand minus summation of all the PIs. Okay, so we will calculate that, and then if we look next basically, so once error has been calculated, so let's see this particular example which we have discussed earlier. Here you can see that some lambda, let's say 4.07 was there, and for that particular lambda 172 and 107.28 was calculated. So instead of 172, we have enforced it to 150, and this 107.28 will remain same. We will not change the P2 in this particular case. So let's say the initial lambda, if I assume the exactly like 4.07, I will get these two values. But for lambda iteration method, I will only enforce this 172 to 150, and instead of 130, I will keep 107. So if I keep 107, I will be short of some megawatts to supply that particular demand of 280. So I will get certain error, and that error will be like 280 minus instead of 172 we have placed 150, and plus it was I think 103, so it has been less. So the error will be positive. If I assume lambda too much high initially, everyone will be producing like uh, a very high power, and the output will be very high. These power values will be very high, and in that case, there is the possibility that it can basically be more than the actual demand. So the summation of pi can be more than the actual demand, and after enforcing the limits, in that case the error will be negative. So once we have calculated the error, we will update our lambda, and based upon the error, so update lambda. So lambda is basically like k plus 1 will be equals to lambda k, and then some alpha and some whatever error we have calculated. Okay, here if our pi is, so again I'm reiterating myself that if summation is less, it means we are producing less, so error will be positive. And if error is positive, uh, this positive error will be added to the previous lambda, and our new lambda will be high, and that encourage the generators to produce more so that this positive error can be minimized. If in, let's say, the initial lambda was very high, in that case generators will be producing more and this error will become negative. If it is negative, then this negative error will reduce the new lambda, and then the output or generator outputs will be reduced. Here this alpha is basically the step size, that how much you are basically uh, change in lambda are basically allowing the change in lambda. And this is very crucial, like, if you change or basically keep very high or very low alpha, your solution will be basically updating um, differently. So this is like, update rule 1. If I talk about another update rule, so which is still a good rule, but will give you answer differently. So it's, let's say, lambda k plus 1 equals to lambda k plus and minus alpha and lambda k. Here the step size is again different. So these alphas in both the rules can have different values. Okay. Here what we are doing is we are basically calculating the lambda k can be basically kept constant and 1 plus minus alpha. So basically, if you look at this particular one, let's say if I keep the take the value of lambda, sorry, alpha here is 0.1. So if it is being added, so it will become 1.1, and then it basically we are increasing the lambda by 10%, and otherwise we are basically decreasing the lambda by 10%. So depending upon the error, whether it is positive and negative, we will use either positive or negative sign. So that's why I have placed both positive and negative. Positive is basically when we want to increase the error. So this positive, negative, like which one we should use, this will depend upon the sign of the error. In this particular rule, we just simply keep, like, plus sign, and the error will itself have a positive and negative sign, so that will be already incorporated in it. And then once it has been done, we can basically check for convergence. Okay. And convergence, basically we will look that the delta change in lambda should be basically less than or equals to some tolerance value, and this tolerance value can be, let's say, 10 to the power -3 or -4, depending upon your requirement and how much accuracy you want. Or sometimes we can also see, like, the error should be less than equals to some tolerance, like, let's say, the error between, like, demand optimal whatever demand we are supplying and the summation of the generations, this error should be less than certain tolerance. So these are, like, I can again say rule 1, either you can use this one or this one. Both of them will work perfectly fine. Here one important note is, uh, whenever we are doing optimization, so this is also, like, derived from the same Lagrangian method and how we can solve it. So whenever we are solving entire process iteratively, generally we consider certain step size. So how the step size basically works, so, like, we have considered a step size here, and that alpha, if this alpha is very high, and this very high is also relative, let me tell you, this very high can also have a relative meaning, like what is the system size, what are, how many number of generators are there. So this very high is also relative, but let's say if this alpha is very high, the change in lambda will be very much, and it will leads to divergence, that our solution will diverge. If this alpha is very low or very low value, then a very slow convergence will be achieved. And if this alpha is, let's say, optimal, then we will have like your algorithm will basically converge in very few or very small number of iterations. So this step size decides everything for this particular kind of methods. Okay, so if you have any doubt so far, you can ask them. Okay. uh, yes, so now once we have obtained this one, now let's look at the loss formulation. So like how to incorporate losses in the system. So what we can do is, let's say network loss modeling. So there is a detailed network loss modeling, and I will just simply use the final outcome of that. So there is, like after a certain approximation, we have come up with a loss formula, which depends upon the power injections. So whatever is the generator power injections, based upon that, we basically obtain a certain loss formula. And that loss formula is basically saying that I equals to, let's say, 1 to n. So if we have n number of generators, and then summation of j equals to 1 to n, and we can say that it's pi, uh, let's say bij, pi, and pj. So this is our quadratic term where two powers are being multiplied, so the rank is 2. Then we have a single linear term as well, that I equals to 1 to n, and this is called beta. So this is not b, this is beta. So generally these are called b coefficients. So let's say this beta or b I naught is basically pi plus some beta naught naught. So this is how, this is a generalized basically linearized version, or a simplified version with certain approximations, that this is how the losses are going to happen if, with respect to the power injection, and those power injections are basically the generator power injections only. So based upon the generators, how much they are producing, this is how the losses are going to behave. So we can write down the economic load dispatch problem here again. So it's minimization, summation over, again, I equals to 1 to n, and ci, pi. So this is the total cost subject to power balance equation, the same equation. So it is like, summation of I equals to 1 to n, pi should be equals to p demand. Now losses are also happening, so I would put losses here, and then the pi should be whatever is the pi maximum and pi minimum. And generally I put a variable here, so all the pi's are my variable. So this is the formulation will look like. And then we can write down the same Lagrangian function. So it is like, pi comma lambda, and this will be summation of ci pi plus lambda, and pd minus pd plus p loss minus summation of pi. So this is our loss formula, and then we can write down delta L upon delta pi, the conditions. So that will be like incremental cost of ith generator, the very first term, then plus certain lambda, and then delta p loss upon del pi, because this loss function is also a function in terms of different pi's minus 1. So this is our condition, and we can solve it further. And delta L upon and delta lambda, which is nothing but our power balance equation same. So it is PD plus P loss minus summation of pi equals to 0. Okay, so we will get these, and this condition is for all I set of n, and that is one condition. Now, how to solve this one? So, I will again use the same approach. Here is basically like, so in lambda iteration method, if I look at this particular equation, you can clearly see that losses are dependent upon the power generation, and power generation depends upon the lambda, and lambda also depends upon the losses, and it's a closed cycle. So if I have to apply the same method, lambda iteration method, I can solve it again, but I will write down the formulation differently, and I will just use the same algorithm and try to write it here. So earlier we basically assumed the very first step was assume something. So assume initial lambda. So we will assume some lambda node. Along with that, we will assume some pi. So let's say p1 node, p2 node, and so on, pn node. So I will assume some power injection as well. Once we have identified these, like power injections, we will calculate. Uh, I have just take a call. So yes. So once we have I like initialized all the power and all the lambda, what we will do is we will see that this is our formulation, right? Where we are basically trying to solve these equations. And if you look at these equations, if this P loss basically depends upon Pi, and it's basically closed loop. Like you have to obtain Pi to calculate P loss, and uh, Pi can only be calculated once P loss is known. So what we will do is we will calculate the initial P loss, and we will calculate the our these incremental P loss. So what I will do is I will with these particular initial values of P note and these, I will calculate the del P loss upon del Pi. Okay, so I can generally we name them incremental losses of, let's say, ith generator. So we will calculate these values. So these values, what will be these values basically? So if you look at, we have had certain formula for the losses, and the formula is basically, you know, uh, depending upon the pi and pj. So we will take a first order derivative of this condition with the p1, then with p2, then p3, and so on. So we'll get different incremental losses, and then we have all the p1, p2, p3, p4 initial values of those functions. So we will use those, and basically try to obtain these values. We will obtain these values, and this when pi is basically whatever is the pi note or initial values. So we will get incremental loss note, I can say. So once we have calculated this one, third step will be basically calculates whatever is the updated values are basically existing values of pi. So far we have initial values, so I will use those, and then if we fix this value here, I can calculate the pi. And if I use this particular equation, and let's say the p loss is known, what I can write down. So if let's say the p loss is known, I can say this is basically 2ai pi plus bi. So that is my incremental cost here. Then plus lambda and incremental loss minus 1. Okay, and ith generator. So I can say the lambda will be equals to so it will be equals to what value? Sorry, pi, not. So the pi will be equals to lambda and then incremental loss of ith unit minus 1 divided by 2ai and minus bi. Am I right? Is this clear that this pi value will be this? No, this is wrong. Look at the equation again and tell me where is the mistake. It's quite obvious, I think. A minus sign should be there, right? Okay, because we have to make it equals to 0, and if I solve it pi, then it will be minus sign. So I can say that the pi is nothing but uh, it's minus minus will become plus. So lambda, okay, and plus how much is the value? So it is basically lambda minus b. I'm is this correct right now? It is still not correct. This sign will not come here. This sign will come here only. Okay. So if it is lambda, then basically we will have you can write it down like this. So it is lambda minus bi minus some lambda and incremental losses of I divided upon 2ai. Now I think it is correct. Okay, so this is what we can write down, and here we know that this is some initial assumed value. We are assuming certain value for this lambda, we are assuming certain value for this lambda, and incremental losses for a particular value of like initial value of p1 p2 p3. We can obtain the incremental losses so far, and we can obtain certain pi. So we can calculate this pi here. So it is basically uh, pi is nothing but lambda minus bi minus lambda incremental losses of ith generator divided by 2ai. So this is how we can calculate. Then this step, this entire step will be repeated here. So I will not write it down. So the fourth step is basically check for like limits. Okay, so we will put those limits, and then we will look for the like fifth condition. So error we will calculate, and the error will be total demand plus total losses. Okay, and minus summation of pi. These losses will be whatever is pi updated. So we have calculated some basically like uh, pi here in the step number 3. Then we enforce the limit in step number 4. So after the output of the step number 4, we will have some pi updated, And for those PI updated values, we can basically calculate the losses as well. So the fixed losses has been calculated, and this is again PI updated existing values. We can calculate error, and then the sixth step is basically update lambda, and we will use the same rules for the lambda update, that either you can use with the error or with certain fixed percentage. And then seventh is basically check for convergence. Some part I think we missed, sent back to, so like with updated lambda, some steps should also be there, and that will be, let's say the seventh step will be check for convert. Okay, wait. What will happen once we have checked for convergence? If node converts, then if not, go back to which particular step? So I will again calculate the second step. Go back to step 2, where I will again calculate the new incremental losses are basically with updated values of the PI. So we have updated certain values. We will again calculate some PI. The same thing we will repeat like earlier. I think I missed one thing. Uh, Check for the convergence, and then seventh step is if a node converged, then can we do it after around 4? Sessions will be going on up to 5, I think. uh, I will take, like, just to complete this one, then I will take 5 minutes of break. So if node converts, then we will go back to the, I think, again same step. Let me see if it is correct. I will go back to the step number 2, and we will repeat it. So far, do you have any doubts in basically economic load dispatch, that okay, we can model this without losses, with losses, and for economic load dispatch problem is solved by a system operator though. So the cost minimization will be the objective for the economic load dispatch, and sometimes we can add emission minimization as well with this particular objective. So we will talk about that when we do some hands-on session. So we will take certain example and try to minimize the emission as well. Okay. So if you have any doubts so far, you can ask. So was a gradient method discussed earlier today in the morning by Dr. Deep Kiran? Jyoti, gradient method was discussed. Okay. Anyone who was present in the morning session, was gradient Newton's method was discussed? Okay, thank you. So I will just quickly wind up this. Yes, so we will look at the first order, method. Uh, how we can use the same method, gradient method. So gradient search method to get a solution for this kind of problem. So we have a Lagrangian function, and that was summation of our cost functions, and plus lambda and PD minus summation of PI. This is actually the same. Whatever we have so far done, it is another variant of that. So gradient is basically first order derivative. So if I write down the gradient of this Lagrangian function, it will have we will have a vector, and that will be like gradient of this with respect to p1, then up to gradient of this or the first order derivative of uh, p2, and basically so on. We can write down delta L upon del lambda. So these are the this is basically gradient, and it is nothing but we have already solved. These are nothing but the KKT condition, like like the first order derivative should make equals to 0. So this we have written down earlier, like with incremental cost of ith generator minus lambda, incremental cost of like second generator, so first generator minus lambda, and so on, incremental cost of nth. Okay, let me make it n. So 1 to basically n minus lambda, and then last part was PD minus summation of pi. So this is the gradient. Now let me define the x. So x in this particular case will be like p1, p2, and up to pn. So these are our variables, and lambda as well. So these are my variables. As we discussed, like the lambda iteration with losses, we solved for like assume some initial value of this. So I will also assume some initial value of this part, and what we can do is basically we can solve the our x problem, and this x k plus 1 will be equals to x k, and minus some gradient, and let's say some step size. Step size is very important. It will either diverge or make it converge optimally. So this delta lambda is basically we are assuming x was equals to some certain x value, and whatever is, let's say, xk. Okay, so this lambda is basically depending upon the x, and all of these will have like p1, p2, p3, and lambda. So whatever is the initial value of x naught, so we will have some x naught, so like p1 naught, p2 naught, p naught, and lambda naught. We will use those values and put those values here in this gradient vector. So this is a vector, and then we will multiply or basically add these vector to the initial value, and we will obtain the new x, and we will just keep on iterating this particular equation, and we can get a solution out of it. So if you have any doubts, yeah, feel free to ask. You can put them in the chat, and I will just take like 2 or 3 minutes break. In a meanwhile as well, like like I will mute myself. You can still put your questions in the chat, and I will try to answer them. You guys have any doubt, you can ask. Okay, so if we have no doubts, we will move to another segment. Basically, like how we can solve it. And so far, we have considered that, okay, we are trying to minimize the generators cost of the generators to satisfy a particular schedule. Now if I look at this, so this is our economic load dispatch. Now another problem is, like, if we want to incorporate the uh, power flows. Okay, so in that case what will happen? So if we look at OPF, uh, with, let's say, same example I consider. So if I'm looking at the OPF, what should be my objective function? It will remain same, minimization of summation of the I equals to 1 to n, and whatever is the cost of the generation. So this is CI and PI. This is, I think, we all agree. Then I have to take care of the power flows. So to obtain the power flows, basically we have to see how much power is flowing in each and every line. So I can say, let's say certain bus is there where a generator is connected, a load is connected, and then it is connected to different, let's say, line segments. So let's say this another node, some generator is connected here, and then some generator is connected to, yeah, let's say this particular node, and then they are connected like this. Okay, so some load is connected here, some load is connected here, and some load is connected here. So let's say this is a four bus system. So bus number 2, bus number 3, and bus number 4. So whenever we are writing down optimal power flow, it basically talks about the power balance at each and every node. So if you have seen, like in economic load dispatch, we have written down one power balance equation. Generally, we call that power balance equation as a global power balance equation. Here, what we will do is we will write down a nodal power balance equation at each and every node. So if I just look at the node number 1, I can say in generalized way that whatever is the power generation of ith generator minus power demand of ith, sorry, PD at the demand of ith generator, that will be injected, a resultant injection into the grid. So this will be nothing but the power injection at particular bus, uh, I ith bus. So like generation minus demand, that value will be injected into the system. If demand is more, then it will become negative. It means we are withdrawing that value. But in generalized way, or just to keep it everything general, we can say that this PGI minus PDI will be injected into the system. If I look at a particular node, you can see that this injection will be going into, like this line and this line. So here what we have to do is we have to provide a summation over J equals to 1 to n. Let's say n number of lines and nodes are there, and Pi to Pj. How much power is flowing from I to J? We have to take care of that, and this we have to write down for all number of nodes. So for this particular example, I can say Pg1 Pd1 will be equals to P12 plus P13. So this is what I can easily write it down. Okay. Then other part is some reactive power flow will also be there. So I can say, QGI minus DI will be equals to summation over J equals to 1 to n, and whatever is the okay, let's me just change these values, like just to see that these are power flows. So PF I J. So this is reactive power flow between I and J, and we will write down for all number of nodes. So I have to write down these this equation for at each and every node in the system. Okay, so we can say that in this particular one, like QG1 minus uh, QD1 will be Q12 or QF12, PF12, PF13 plus QF13. So this is for first node, and similarly you can write down for another node. Whenever at bus number 3 and 4 there is no generation, so we can keep this PG and QG equals to 0. It's that much simple. Once we have identified this part, uh, we have to look for the another constants that, and we had one condition, like okay, another condition is like these variables should be within the limit. So our in economic load dispatch we had that our PGI should be PGI maximum, and this should be PGI minimum value. So this was quite obvious that generation should be within the limit, and then we had our QGI that should also be whatever is the maximum and minimum limit. Okay, so we'll write down these equations as well. Then we will check for the another limits, and those limits are basically that power flow limits, like certain lines have line rating. So depending upon what kind of rating we are considering, whether it is megawatt rating or MVA rating of the line, depending upon that we can identify the line rating. Let's say we are only looking for the megawatt rating, then I would say PFIJ should be less than equals to whatever is the PFIJ maximum value. And then similarly, so line has same capacity in both the direction, so it should be more than the negative of PF maximum. Okay, so the power flow can be in either direction. So the minimum, let's say if line has a 100 megawatt limit, then the power flow in that line can be either positive 100 or negative 100. Okay, so this is the minimum and maximum limit. So this is a very fundamental optimization problem for the optimal power flow. The thing is, if you look at this particular problem based upon different assumptions, we can basically divide that entire problem. Here, these two are basically certain names we have. So this is called nodal. So we are writing it down at every node. So this is nodal, active, power balance equation. This is again a nodal, reactive power balance equation. Okay, so this is our reactive power balance equation. This is our nodal power balance equation, and these two are basically power generation limits. And this is our power flow limits. Power flow limits. If you look at this particular formulation, one very important point I wanted to highlight, like we on very first day we basically looked at the process of optimization, and that process included, I think, 6 or 7 points. The very first was identifying the problem is, then based upon the problem we have to identify the objective function, and then what can be the different constants. Then we will look for basically look for what type of problem it is, whether it is linear, non-linear, mixed integer, and all type of the problems. And once we have identified that one, then we will choose a particular solver or a basically tool to solve that particular problem. Once we have identified a tool, we will solve the problem. And the entire thing in the optimization depends upon how you are formulating the problem. Now, if you look at this particular problem, I can say, okay, let me change the color. What are the variables here? Can somebody tell me what is the variable? What are the variables here? So in any optimization problem, we have to define certain variables. So what is X here? And then what extra are basically what the different values which we have to provide them as a input. So can anybody tell me what is the input here or variable in this particular problem? So Anand has said that so far P and Q looks like variable. So if I can say that all the uh, PGI and QGI is variable. So I can assume some certain parameters as well. Parameters are input basically. So parameters I have to supply to the problem, and variables will be the output of the optimization problem. That okay, these are the variables, and give me the optimal value of these variables. Okay, so this is how we are proceeding. So parameters generally we consider our demand, active and reactive power demand is my parameter. I can say that generator limits can be the parameter. So I can max P active power generation of all the generator, whether it is maximum limit or minimum limit will be parameter. The reactive power for all the generators, maximum limit and minimum limits are basically defined by the unit that what it can have. It can have this much maximum value and minimum value. So these are also my input parameters. Line flow limits, yes. So power flow of all the lines, uh, maximum value is also parameter. Okay, and then anything else which is parameter here. So let me give you one more thing as a this post function. Generally, the value of this post function is AI pi is okay. AI pi square plus bi pi plus ci. So these cost coefficients, so it is p gi gi and pgi. Okay, so these values will also be abc will also be your parameters. So the cost coefficients ai bi and ci will also be the input parameters. Apart from that, do you think some like is missing? Maybe I must have forgotten some value. Very first parameter will be like number of units. Okay, and for all of those number of nodes basically, so number of nodes which is defined by n. So in the entire system we have to provide the n number, that what is the number of nodes in the system. And for all of those nodes we will get the pdi and qdi as a parameter. And if some generations are there, then pgi and qgi will also be known to us. Anything else which is missing? Can you solve this particular problem? The answer is yes or no. Line flows. So pfij. So whether it is parameter or variable. So this one part is like, if you look at, I have counted everything here. If I start from this particular part, this I is just index, and I have accounted that n is my number of node, and this will be the parameter. Then a, b, and c is my parameter, and some pgi I have written. uh, no, I'm just asking this pf whether it is parameter or variable. That's it. This is what I'm asking. This pfij, this part, whether it is parameter or variable. So if I look at like a, I have defined that okay, I have to supply this a because it is parameter. Pgi I have defined as a variable, that okay, I will get as a output. B as well and c as well, so these are input, pgi is the output. If I look at this particular pgi is my variable, pdi is parameter, I have defined it. uh, pfij I have not defined so far. So whether where should I put it, in variable or in parameters? Any answer? So there is one answer, like response that it should be variable as per the problem formulation requirement. So the thing is, if just yes, some quantities are known, some quantities are unknown, and if I check only pfij and qfij is left to be like designated either as a variable or parameter, and everything else has been accounted for. I think all the syntax we have used here. So just just think about it. If this pfij is parameter, and if I supply this one, then look at this particular diagram. This pf 12 here, and this pf13 will be known, and as pd1 is also parameter, if it is known, pgi is no longer variable, it will have fixed value. So we are sure basically that this pfij should also be a variable. So to be very honest, whatever the mathematical formulation we have written here, we cannot solve it so far because we have not linked our existing variables to this pfij. So we know that pfij are basically will depends upon the variables, but we have not linked it. So if you have not properly bounded the problem, this problem or basically this particular problem will be unbounded. You will get any solution if you write it down like this. And let's say if I keep this pf and qf as a variable, this problem is unbounded, and you will like not get any solution out of this particular problem. So in optimization, we have to make sure that each and everything is linked, and otherwise that will be redundant. Okay, so this pf value can be anything. If I does not link these pf values with pi and qi, then it will have any random value. uh, Obviously it will always satisfy the pmax, and we will not be able to basically get any solution out of it. At least that won't be the optimal one. So what we know so far, I think, like if you all are like power, I'm assuming that you have some basic fundamentals of power uh, system. So power flow analysis, like earlier in the lecture we talked about that there are simulation and there are optimization, and simulation has certain tasks, and the optimization will have certain attributes, and simulation has certain attributes. And we gave example that the simulation is basically power flow analysis, and optimization is basically optimal power flow at basically decision, like we optimize the power flows. So yes, so the one of you answered that line flows will be from load flow problem. So I can write down like this pfij. So this will be what I think vi, vj. So this is magnitude yij magnitude. Then I think it was cosine of theta ij minus delta j plus delta I. So this is what and how we can define it. So similarly, I can define the Q of ij as well. It will be negative of Vi, Vj, Yij and sine of theta ij minus delta j plus delta I. So this is what we can define it. So basically, these are the magnitude. Okay. So now what happens here? Once we have defined these values, I can use these two formulas and put here instead of QFIJ and PFIJ above. So once I use them, uh, I have to provide certain more information. You can see VI, VJ, YIJ, theta IJ, delta IJ, and theta IJ and delta I or delta J are also now part of our optimization program. So if I replace this uh, QFIJ with the given formulation and this PFIJ with the given like equation, then I have to further define certain variables. Now you can see that the voltages here are also variables, because depending upon the power flow, basically the how much power is being generated, the voltage is on each and every bus will change. So this Vi and delta I are also variables. Okay, so once we have defined that, okay, this Vi and delta I is also variable, then some parameters that we can say that this Yij magnitude and angle of this particular theta ij is also parameter, that this is from the y bus. So this is nothing but the elements of y bus matrix, and y bus matrix gives me the topology. So if you do not provide that y bus information or the topology information, the mathematical optimization will not know that these there you have four generate are basically two generators, and four number of buses are there, and how they are connected and what is their reactance, resistance, everything is not known to the mathematical problem. And the power flows will depends upon the resistance reactance value of the line. Like power always follows the low impedance path, right? So it will you have to provide that impedance information, and that is available from the y bus. And y bus also gives you the topology, because based upon topology we basically create the y bus matrix. So once I have provided that information here, I have to modify some equations. So this PFIJ will be replaced by this value, this PFIJ will be replaced by this value, and QFIJ will also be replaced by this particular value. Now there are two more variables, so I have to provide the limits of those variables. So I have to put the limits. So we have a certain Vi and delta I. So I will put that the Vi should be have a maximum value and minimum value, and delta I should also be having some maximum and minimum value. As it is angle, so we can say, let's say pi, and minus pi is the maximum and minimum value. So I have to provide that parameters are basically Vi, max, and min as well. So these are also one of my parameters, and then we can solve this particular problem. There is one more issue. Basically, these angles are always calculated with respect to a reference. Without reference, you can never calculate the angle. Angle is always with respect to reference. That okay, there are voltage vectors, there are power, and all of these like complex numbers are there, and they have certain angle associated with them. So that angle can only be calculated with respect to reference. So we have to provide one more condition, that theta I, or basically whatever is the theta I, should be equals to 0. Now here I have to mention third part is that this I is equals to reference node. Okay, so this I have to write down for all I which are basically reference node. So if I have, like how many reference node we have in power system, like we try to solve a problem, how many reference we have. So some reference node. So yes, we have one slack bus, so one reference bus is there. So whatever is the number of, let's say bus number 2 is my slack bus, so delta 2 should be equals to 0. Okay, if bus number 1 is my slack bus, then delta 1 will be equals to 0. So this is how this is so far, like looks like a problem which can be solved. And if you see, everything is linked now. So this PGI and PDI is parameter, but this variable is dependent upon the voltages. So these are linked. These voltages will affect the QF. So QGI decision will be affected by the voltages. So if I just look at the optimization function only have one variable, which is PGI, power generation, active power generation, and other four variables, which is reactive power, voltage magnitude, and angle, voltage angle. They are not part of the minimization function. Okay, so I can simply minimize the PGI from there if there is no linkage. So I have to place linkage with each and every variable. If there is no linkage between multiple variables, if there is no dependency, then the variables which are not depending upon the decision variables, and in this particular part the objective function will decide what are the decision variable, and objective function is just having a PGI value, which means active power balance or active power generation is my decision variable. I have to look for that only, because that variable is only affecting my objective function in this particular formulation. So PGIMI is decision variable, and rest of the variable should basically directly or indirectly depends upon PGI. Otherwise, if some variables are there, they can have any value. They are not affecting PGI, they can obtain any value. It will not change my objective function, which is cost, and it will not affect at all basically. So whenever we are writing a optimization problem, everything should be linked. Okay, and objective function should be in such a way that whatever is the variables in the objective function, those variables should be uh, linked with each and every variable. If any random variable which is not linked directly or indirectly with the decision variables which are in objective function, then that particular variable can attain any value, and it does not have any significance in our optimization problem. So many of you are, like doing research, many of you are basically teaching. So whenever you are formulating any problem, make sure that everything is linked. Here if I say only PGI is my decision variable, so PGI is equals to power flow Ij, and power flow Ij is basically depends upon Vi and delta I. So Pij is linked with voltage and angle of the bus. Then voltage and angle will change. So this voltage and angle values are dependent upon PGI. So based upon the value of PGI, power generation or active power generation, the voltage angle and magnitudes are going to affect it, and those affected values will then further affect the reactive power QGI as well. So PGI and QGI are also linked. Otherwise, like if I do not put these two values like power flow in terms of voltage and angles, both of these equations are independent. You can easily solve them separately. You don't need put them everything in one optimization problem. Then so PGI is has having the limitation of maximum minimum. QGI indirectly be affected by the PGI, will can also have certain minimum and maximum limit. Then PFIJ is again dependent upon the voltage and angle, and it will be restricted by PF max. So this PF max will also play some role in deciding PGI. So each and every parameter here will play certain role in deciding PGI. So like like this delta I equals to 0. So whatever is the reference bus angle, if that becomes 0, that will affect the PI and QF, PFIJ and QFIJ. That will affect the PGI, and that will affect the post function. So each and every variable should affect the post function. This is very important. So if you look at this particular problem, let me give the equation number. So let's say this is equation number 1, this is equation number 2, this is equation number 3. I have missed one part here. Let me erase this and this and write down again. Okay, so this equation we have to write down for all I set of generators. So if we have n like say let's say some certain number of generators, so this equation we have to write down for all the uh, generators. This again we have to write down for all the generators, and these are basically power generation limits. Then if we come back, this equation will be written down like line flow limits. So this will be written down for all ij pair. So like I and j are node numbers, so line will be represented by a ij pair. So all ij pair should be set of number of, let's say, lines. Okay, and then this has to be like for all I a set of number of nodes. Like for each node we have to write down this should be for all I set of node, and this we have already defined that this is for all I equals to reference node. So this is how we write down any generalized optimization problem. Like we make sure each and every information, everything is provided here. And if I name the equation, so this is equation number 2, equation number 3, equation number 4, equation number 5, and this PF ij and QF ij will take the values above. So I will not mark them as equation because I don't need this PF ij and QF ij in my formulation. Then equation number 6, 7, and 8. These equations gives the model of ACOPF. Equation number 1 to equation number 8. This is my ACOPF model. Okay, here we are basically looking at each and every problem and the ACOPF. This is how we will write down the ACOPF problem. Do you have any doubts so far? So in ACOPF, we basically the objective function which we have considered is basically what was the minimization of cost. This objective function we considered. Sometimes we can have another should QF limits be considered. Generally, the limits which are provided are either megawatt limits like active power limits, sometimes MVA limits like so apparent power limits, and manufacturer does not provide the reactive power limits. Usually, like if you see in a line, we do not operate with a very low power factor. It is like let's say a line is being designed, some voltage and current. So we can say the line has a limit of MVA rating, mega volt ampere. And if certain power factor is defined, let's say 0.8, 0.9, 0.95 or something, the most of the time are the basically major chunk of the power which is flowing in the line will be active power only. And reactive power is basically supplied by the local sources as well, like we have capacitor banks and all at the load side. So we supply that with the reactive power will be supplied by those sources. So we either look for the active power limit, because that is the most are basically this is what we are interested. We are paying for our active power only, not for the reactive power. uh, okay, so that's why the active power is of the concern, that we have to optimize that. We want to optimize our entire network to the best extent, that okay, if some maximum, so let's say in particular line has very low impedance, so most of the power in the entire network is trying to flow to that particular line. So we would like to utilize that line to the best extent. So we will try to like have a maximum active power flow through that particular line. If MVA ratings are defined, let's say mega volt ampere, then this particular formulation will change. Instead of this PF, like instead of equation number 5, we can change. So like equation number 5 was like PFIJ, and PFIJ was defined as some values. So whatever is the PFIJ max, and then PFIJ max minimum, this was defined. Instead of that, sometimes we go for the apparent power, and apparent power is what basically like PFIJ plus J, QF ij magnitude, or I can simply put a square less than equals to whatever is the ij maximum capacity square, and similarly and the other way around. Okay, it is a square, so I don't need the less than condition. It can be basically both the direction, minus sf sfij and plus sfij will be satisfied by this one. So the magnitude basically should be less than the MVA capacity of a particular line. Usually, like what is preferred is either active power limit, and sometimes we also look for the current limits. Okay, and generally this active power limit we considered for the transmission network, and distribution networks are defined for the current carrying capacity, like all the feeders. If we have those feeders are defined for current carrying capacity, so that's why we have this current limit, and this is for like distribution network we define in terms of current. Usually we do not define reactive power limits and apparent power limits for the optimal power flow. Usually we either go for the active power limit or current limit, and generally it is defined like in transmission it is active power flow limits, and in distribution we define current limit. Okay, so I think I'm able to answer your question. Okay. If you have any more questions, any one of you, you can add, put that question there. Okay, can somebody tell me? Sometimes we can have a function of minimization of total losses. The objective function can be is basically minimization of total losses. Network losses, like we want to minimize the network losses. So in OPF, so we are still wants to optimize everything. The power flow should be optimized, the voltages should be within the limits, the generators which are producing should be within the limits. So the constraints, like above we have written down equation number 1 to 8. So equation number 2 to 8 are the conditions. 2 to 8 will remain same. Our objective function will change. So instead of like minimization of the total cost, we can have a objective function of total network. Can anybody tell me how we can calculate the network losses in this particular case? So like this part is here. So I have this particular case. And network losses means, again, I am talking about only active power losses, not the reactive power losses. So this is my objective function. Uh, Instead of this CI PGI, I will put the losses in the network. And what will be those losses? How can I calculate the losses? Is there a losses, like, you should put the loss formula, or the losses are already there? So So we have to look it very judicially. Let's consider an example. It's better to have an example. So let's say I have a network, a single generator here, certain demand here, some generator at this particular node, and some demand is this particular node. Generator bus number one, bus number two, and some line is there. So let's say if we want to write down OPF, so all of those constants were there, and let's say if I write down the constant number 2, that was PG1 minus PD1 equals to PIJ, and we know that the PIJ has been defined like V1 and sorry P12, because only 1 and 2, only one line is there, so it will be P12, and that will be V1 V2 Y12 cos of theta 12 minus delta 2 plus delta 1. I think we all agree for this particular formula. Okay, then I can write down Pg2 minus Pg2 equals to P21, and that will be equals to V2 V1 Y21 cos of theta 21 minus delta 1 plus delta 2. Is this clear? Okay, similarly, you can write down for reactive power and all. I am just writing down the active power balance equation, and you can see I have to write it down for all number of nodes. So in this particular example, the number of nodes are 2, so I have written it 2 times. Okay, so basically what we are doing is we are looking at this particular node only, and this is my P12. And when I'm writing down the nodal power balance equation at node number 2, this is P21, like power from the second node. If I add them up, let's say add these equations, I will get Pg1 plus Pg2 minus PD1 plus PD2 equals to P12 plus P21. This is what I will get. Okay, and I can further simplify, let's say rearrange everything. So what I can do is I can say this is nothing but equals to the total demand, and let's say that is capital PD. So I can say PD sorry. So I can simply say that it is summation of I1 equals to N, which is equals to 2 in this case, PGI minus PD equals to P12 plus P21. So what is this term represents? Can anybody guess? With the context, I think you should be able to answer that what does this term represents? Anyone else? Ankit, anyone else wants to answer? What does it represents? So we have gone through this particular formulation earlier in the economic load dispatch, and if you see, I can write it down like this: summation of pi minus pd equals to p loss. So this p12 is nothing but the like addition of p12 plus p21 is nothing but the losses. Okay, so this term represents loss function. Okay, so this is nothing but the loss, and in generalized way I can write it down like uh, pair ij set of l number of lines. So I am doing a summation over all the ij pairs. Okay, and that pij plus pji I can put here, and that will be the network losses. Is this clear? Okay. Another way I can write it down like this as well. Let's say P I equals to 1 to n, and then j equals to 1 to n P I j. Okay. So if you look at this particular part only, let's say when the term becomes negative, what does that signifies? Uh, we will see whether it will become a negative or not. So if I just simply look at this one, whether this term, whatever I have written, represents this or not. So it is nothing but like for I equals to 1, so it will be p1 1 plus p1 2 plus p2 2, sorry, 2 1 plus p2 2. So if I just remove this, this is nothing but the p basically a 1 2 plus p2 1. Is this clear? Okay. So this is how basically we can write it down here. One interesting thing is like with this particular y bus um, part, and when we try to write it down, if pij is represented with whatever we have mentioned here, if this is how the pij has been used, then we can also write it down like this. These values will also be basically also part of it, and they will be cancelled out, and we will get the overall network losses. So this is how we can write down the losses, or you can also write it down like this, because shunt components are also there. So these p11 represents basically if some line is there, let's say some generator is there, some load is there, and some another line is going to some let's say ith node to j equals to, let's say, 1 to n, and some shunt capacitance are also being considered. So this p11 or pii or pjj will basically represent the shunt power. So that is also basically included, and it will not have any impact, but the overall loss minimization and losses can be represented by this. uh, will this value be negative? That is one comment that will this be a negative value? I don't know. So we all agree that if I send some power from 1 to 2, some losses will happen, like in the line. Okay, so some losses will be there, I square r losses. So let's say these losses has been placed, and we will get some of the less power at P21. So if I am sending, let's say 100 from here, I will get 98 there. Let's say 2 megawatt has been in the loss. Can you tell me what is P12 here? 100. And what is P21? Minus 98. It is other way around. And if I add them up, it will be the losses, and that is equals to 2. It's simple. So you will never get a negative value. Okay. There is one question. What will happen if the term becomes negative? What is signifies? But if you are calculating the network losses, it will never be negative. It will always positive. Network losses can never be negative. If some power is flowing, some losses will also be there, and those will always be positive. It can never be negative. Other way around as well, like like if you similarly send some power from this side, uh, you can have those values, and whatever is the power, it will be like one power is basically opposite of other, so the summation will always be a positive value. Is this clear? Yangya, and am I able to answer your question? Right, so the losses will always be positive, they will never be negative, and it is quite like we can apply the common sense as well, that the losses should always be uh, what positive. So this is how, with this particular example, we have seen that okay, the losses will be positive. So if I have to write down this ACOPF problem with the loss minimization, what I can do is uh, okay, so the ACOPF can be like minimization of network losses. So I equals to 1 to n, and j equals to 1 to n, and we can basically define Pij. Okay, so Pij is basically our losses, and subject to we have equation 228 which we have defined earlier, and we have to define Pij, that Pij is nothing but VIVJ Yij cos of theta ij minus delta I plus delta j. Either this, or you can simply put this value, like instead of writing down this particular equation, you can directly place this value here, and we can have a ACOPF with loss minimization objective, and the rest of the constants will remain same. Equation number 2 to equation number 8. Is there any doubt so far? So we have learned how to model a particular optimization problem. What we should always see. So whenever like I have explained that to you, that this problem is not complete. It will not give you the optimal solution. We have to define basically the dependency of certain, like this even if I write down like this these two equations which I have mentioned here, I can define like that only, like I can have two more extra equations, and I have defined that this PF and QF are this. So I have made that dependency. I can use those as extra equations, and then I can have like PF and QF as a dependent variables as well. But yes, I don't don't want to create more number of variables. So I would generally replace them. Okay, so this is basically replace replace as per these values. Okay, PF and QF. So the linking should always be there. Otherwise, like some of the constraint may be uh, not useful. We can basically call them redundant. Some of the variables may be redundant. Even if you write down those as a part of your optimization problem, they will not have any impact on the objective function. And if they do not have any impact on the objective function, whatever value they attain, it does not matter to our final decision. Okay, so the decision making is how much a generator should produce or how much active power a generator should produce for this particular case. Okay, and reactive power will depends upon that because it is a secondary output or basically byproduct of cost minimization objective. So any doubts so far? We will end today's session if don't have any doubts. So tomorrow is 5th. Okay, let me see. So tomorrow, what we will do is I will explain DCOPF. So today, like this time I went with the ACOPF first because I wanted to focus more on the how to read optimization and how to formulate the optimization problem. Okay, so yes, we have explained that each and everything should be linked. Otherwise, they will not have any impact on the objective and they will be redundant from the optimization problem point of view. So the ACOPF is complex, so that's why we have went with this one. Tomorrow morning we have a 10 to 12 session. In that, basically, we will talk about the linearized version, how we can linearize this one. What are the different assumptions? Maybe I think Yangya was already attended the previous FDP, which was on OPF, and many of you others as well. So in that we have discussed all of these. So but yes, every time if I teach something, I always come up with some other method. So I would recommend that you should attend and then engage and ask the questions if you have any. Then in the evening session we will try to you know have a hands-on experiments with the MATLAB. Okay, like how we can solve this our economic load dispatch problem, how we can solve the DCOPF and ACOPF. So I will try to basically uh, solve those problems as a in MATLAB. So we will have those sessions tomorrow. Thank you very much. If you have any doubts, still you can always email me. If maybe I think a few of you are not present, so we will share the uh, YouTube link with you. You can watch them, and if you have any doubts, you can always email me. I will try to answer them. Thank you.